10. Hello students. Today we'll start with the types of reactions. There are 4 types of redox reactions: combination reactions, decomposition reactions, displacement reactions, and disproportionation reactions. So first to start with, combination reactions. Last class we discussed about redox reactions, and I defined redox reactions as those reactions in which both oxidation and reduction reactions take place simultaneously are called as redox reactions. So to start with the first redox reaction, here combination reactions. When two elements or one element with a compound combine to form another compound, redox reaction takes place and it is called as combination redox reaction. For example, sulphur combines with oxygen and it results in the formation of sulphur dioxide. Here, sulphur and oxygen both are present in their elemental state and they are having an oxidation number of 0. Sulphur from 0 state, it goes to +4 state. So sulphur is undergoing here oxidation, and oxygen is going from 0 state to -2 state, and oxygen is undergoing here reduction. So here both oxidation and reduction reactions are occurring simultaneously, and two elements are combining with one another, resulting in the formation of compound, and it is a type of combination redox reaction. Similarly, another example is magnesium combines with oxygen to form magnesium oxide. Here, magnesium is undergoing oxidation from 0 state to +2 state it is going. So it is undergoing oxidation, and oxygen 0 to -2 state, it's undergoing reduction. So this is another case of combination reactions. Similarly, hydrocarbon, when it burns in oxygen, here C2H4 plus O2, it results in the formation of carbon dioxide plus water, CO2, it is CO2 plus H2O. So this is another example of combination reactions. Next, I come to decomposition reaction. In decomposition reaction, when a reaction involves breaking of a compound into two or more components, at least one of which must be element, that is called as decomposition reaction. And it's also a case of redox reaction. You can take the example water. It undergoes electrolysis and decomposition reaction takes place, resulting in the formation of hydrogen plus oxygen. Here in water, hydrogen is present in +1 state and it's going to 0 state, undergoing reduction, and oxygen from -2 state, it goes to 0 state there. So here both oxidation and reduction reactions are occurring simultaneously, and that's why this is a case of redox reaction and it is a decomposition reaction. Another example, ammonia undergoes decomposition reaction and it results in the formation of nitrogen plus hydrogen. 2NH3 gives N2 plus 3H2, in which nitrogen is undergoing reduction from -3 state, it goes to 0 state, and hydrogen from +3 state, it goes to 0 state, it undergoes reduction. So those reactions in which oxidation and reduction occur simultaneously, nitrogen is undergoing oxidation here and hydrogen is undergoing reduction here. So such reactions are called as redox reaction, and it's a case of decomposition reactions. One compound, it is breaking into two or more components. Hope it's clear. The third type of reaction I would like to discuss is displacement reaction. So those reactions in which an ion or an ion in a compound is replaced by ion of another element is called as displacement reaction. And these are of two types: metal displacement reaction and non-metal displacement reaction. Metal displacement reaction, when more reactive metal displaces less reactive metal from its salt solution, that is called as metal displacement reaction, and it is a case of redox reaction. Let's consider an example. Iron combines with copper sulfate to form copper plus FeSO4. Iron here is present in 0 state and it goes to +2 state there. So iron is undergoing oxidation and copper from +2 state is going to copper in 0 state there. So this is undergoing reduction. So those reactions in which oxidation and reduction reactions take place simultaneously are a case of redox reaction, and it is a metal displacement reaction. This is a case of metal displacement reaction because the metal that is present above in the reactivity series that displaces the metal that is present in the lower series from its salt solution. So this is a case of displacement reaction. Another example, you can see copper reacts with silver nitrate and it forms copper nitrate plus silver. Copper from 0 state goes to +2 state, so it's a case of oxidation, and silver from +1 state goes to 0 state, so it's a case of reduction, and silver is being displaced. So this is a case of metal displacement redox reaction. Let's see the second case, non-metal displacement reaction. When more reactive non-metal or metal can displace less reactive non-metal from its salt solution, it is called non-metal displacement reaction, and it's a case of redox reaction. Take the example, 2 KBr plus Cl2 gives 2 KCl plus Br2. 2Na plus 2H2O gives 2NaOH plus H2. Since non-metal is displaced, this is a case of non-metal displacement reaction. The fourth type of reaction I would like to explain is disproportionation reactions, and you should have a very clear-cut idea of this disproportionation reactions. So disproportionation reactions are those reactions in which an element in one oxidation state is simultaneously oxidized as well as reduced. That is, its oxidation number is decreased as well as increased. Also, you can say self-oxidation and reduction takes place, and such reactions come under disproportionation reactions. A simple example I would like to explain here you about is hydrogen peroxide goes to H2O plus O2. 2H2O2 gives 2H2O plus O2. This is a reaction in which you can see here oxygen is the oxidation state of oxygen in H2O2. Since it is present in peroxide state, it is present here in -1 state. And in H2O, it goes to -2 state. So from -1 state, it goes to -2 state. This is a case of reduction, and same substance, that is oxygen, from -1 state in peroxide state, it goes to 0 state, oxygen in 0 state. So this is undergoing oxidation. So the species in which the same substance undergoes self-oxidation and reduction means this is undergoing oxidation as well as reduction. Such reactions are called as disproportionation reactions. This is a simple example of disproportionation reaction I had given. Next, look at this question. The question is, justify that the reaction 2Cu2O plus Cu2S gives 6Cu plus SO2 is a redox reaction. Identify the species oxidized, reduced, and also which acts as an oxidant and that acts as a reductant. So here you see, when you calculate the oxidation and when you assign the oxidation number to each species that is in this reaction, you can calculate in the first case for 2Cu2O, copper is present here in +1 state, cuprous oxide it is, copper is present in +1 state, and it goes to Cu state. From +1 state, it is going to 0 state. So this is undergoing reduction. And sulphur in Cu2S is present in -2 state, and it's going to +4 state, that is sulfur dioxide, +4 state. So it is increase in oxidation number. So it's a case of oxidation. So here copper is undergoing reduction and sulfur is undergoing oxidation there. And so this reaction is a case of redox reaction. Now look at CO2O helps sulfur in CO2S to increase its oxidation number. Therefore, copper in +1 state acts as an oxidant, and sulfur of CO2S helps copper both in CO2S itself and CO2O to decrease its oxidation number. Therefore, sulfur of CO2S acts as a reductant. Hope this question is clear to all. Let's look at the next question. The question is, which of the following species do not show disproportionation reaction and why? ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. Also write reaction for each of the species that disproportionates. So here ClO4 does not undergo disproportionation reaction because in this oxoanion, chlorine is present in its highest oxidation state, that is +7. And the disproportionation reactions for the other three oxoanions of chlorine are, you can see, 3ClO minus gives 2Cl minus plus ClO3 minus. So here Cl is present in +1 state, goes to -1 state, undergoing reduction. And from +1 state, it goes to +5 state in ClO3 minus. So it is undergoing oxidation. So this is a case of disproportionation reaction. The second case you see, 6ClO2 minus gives 4ClO3 minus plus 2Cl minus. Here Cl is present in +3 oxidation state and it goes to +5 oxidation state in ClO3 minus, undergoing oxidation, and it goes from +3 state to -1 state in Cl minus, and it is undergoing reduction. So it's a case of disproportionation reaction. Similarly, 4ClO3 minus gives Cl minus plus 3ClO4 minus. So here in ClO3 minus, Cl is present in +5 oxidation state and it goes to Cl minus in -1 oxidation state, undergoing reduction. And from +5 oxidation state, it goes to +7 oxidation state in ClO4 minus, undergoing oxidation. So this is again a case of disproportionation reaction. So ClO4 minus only does not undergo disproportionation reaction because it is a case of oxidation state of chlorine in this oxoanion is present in its highest oxidation state of +7 respectively. Hope this question is clear to all. Let's see this next problem, and the question is, suggest a scheme of classification of the following redox reactions. The first one, as you can see, nitrogen combines with oxygen, N2 plus O2 gives 2NO. This nitrogen is combining with oxygen to form nitric oxide. So naturally, this is a case of combination reaction, combination redox reaction. Look at the second case, lead nitrate, 2PbNO3 twice gives 2PbO plus 2NO2 plus half O2. So lead nitrate is undergoing decomposition reaction and it results in the formation of lead oxide, nitrogen dioxide, and oxygen respectively. So this is a case of decomposition redox reaction. Next, third case you see, sodium hydride combines with water to form sodium hydroxide plus hydrogen. Since hydrogen has been displaced here, this is a case of displacement reaction, displacement redox reaction. The next case, 2NO2 plus 2OH minus gives NO2 minus plus NO3 minus plus H2O. So here nitrogen dioxide is going to NO2 minus state, right? And NO3 minus state. So this is a case of disproportionation reaction. Here nitrogen from +4 state, it's going to +3 oxidation state. So this is undergoing reduction, and nitrogen from +4 state is going to +5 oxidation state in NO3 minus. So This is a case of disproportionation reaction because the same species nitrogen here is undergoing self-oxidation as well as self-reduction. So this is a case of disproportionation redox reaction. Hope it's clear to all. Next, let's come to the topic, the paradox of fractional oxidation number. Sometimes when you calculate the oxidation number of a species, it comes out to be in fraction. So that is, let us check, that is the paradox of fractional oxidation number. Let's look at the examples. Here it is C3O2. When you calculate the oxidation number of carbon, here it comes out to be 4/3. Similarly, in Br3O8, when you calculate the oxidation number of bromine, it comes out to be 16/3. And Na2S4O6 sulfur oxidation number comes out to be 2.5. So the idea of fractional oxidation number is unconvincing to us because electrons are never transferred in fraction. Actually, this fractional oxidation state is the average oxidation state of the element under examination. So if you look at the structures, then it will be clear to you that why we get the fractional oxidation number. Here, when you look at the structure of C3O2, carbon suboxide, average oxidation number comes out to be 4/3. But when we draw the structure of it, this is the structure of C3O2. First carbon is present in +2 oxidation state. Second carbon is present there in 0 oxidation state. And third carbon is present there in +2 oxidation state. When you take the average of it comes out to be 4/3 respectively. And that is actually the average oxidation state of the element which we get. Then when you look at the structure of Br3O8, this is the structure of Br3O8 in which the first Br is present here in +6 oxidation state. Second Br is present there in +4 oxidation state. And the third Br is present here in +6 oxidation state. So 6 + 4, 10 + 6, 16/3. That is the average oxidation state of this tribromo octaoxide. Similarly, when you look at the structure of S4O6 2-, that is tetrathionate ion, sulfur is present in +5 oxidation state. Second sulfur is 0. Third sulfur is present in 0 oxidation state. And fourth sulfur is also present there in +5 oxidation state. So overall, the average oxidation state of the sulfur comes out to be 10/4, which is 2.5 respectively. That is the average oxidation state of this sulfur there. And this is the paradox of fractional oxidation number. Let's discuss the question, why do the following reactions proceed differently? Here you see Pb3O4. When it reacts with HCl, 8 moles of HCl, it gives 3 moles of PbCl2 plus Cl2 plus 4H2O. Whereas when the same compound Pb3O4 reacts with nitric acid, 4 moles of HNO3, it gives 2 moles of lead nitrate, 2 PbNO3 twice, plus PbO2 plus 2H2O. So why do the following reactions proceed differently? The answer to this question lies in Pb3O4 is actually a stoichiometric mixture of 2 moles of PbO and 1 mole of PbO2 respectively. So 2 moles of PbO plus 1 mole of PbO2 is equivalent to Pb3O4. So in PbO2, lead is present there in +4 oxidation state, whereas the stable oxidation state of lead in PbO is 2. PbO2 can act as an oxidizing agent, and therefore it can oxidize Cl- ion of HCl into chlorine. So there are 2 types of reactions which occur when Pb3O4 reacts with 8 moles of HCl, forming lead chloride plus chlorine plus 4H2O. So since PbO reacts with, it is a combination of PbO, 2 moles of PbO and 1 mole of PbO2. So 2PbO plus 4HCl gives 2PbCl2 plus 2H2O. This is an acid-base reaction that is taking place. And the second split up reaction of this is PbO2 combines with 4HCl, and since it acts as an oxidizing agent, redox reaction takes place, forming PbCl2 plus Cl2 plus 2H2O. Whereas nitric acid itself acts as an oxidizing agent, therefore it is unlikely that the reaction may occur between PbO2 and HNO3. The acid-base reaction occurs between PbO and HNO3. So PbO reacts with HNO3 to form 2PbNO3 twice plus 2H2O, and PbO2 is passive in nature against HNO3. Thus, it makes the reaction different from the one that follows with that of the HCl. Hope this problem is clear to all. Let's now discuss the paradox of oxidation number questions. Look at the question. Question is, what are the oxidation numbers of the underlying elements in each of the following, and how do you rationalize your results? Ki3, H2S4O6, Fe3O4, CH3CH2OH, and CH3COOH. First, let's discuss for Ki3. In Ki3, oxidation number of potassium is +1. Therefore, the average oxidation number of iodine comes out to be -1/3. But as I said, the oxidation number cannot be in fractional. Therefore, you should consider a structure, and the structure is K plus I2, and one I is held together with coordinate bond I minus. So here a coordinate bond is formed between I2 molecule and I minus ion. The oxidation number of 2 iodine atoms forming the I2 molecule is 0, while that of iodine forming the coordinate bond is -1. Therefore, the oxidation number of 3 iodine atoms in Ki3 are 0, 0, and -1 respectively. And therefore, we get the average oxidation number of iodine here as -1/3. But when you draw the structures, here you come to know that iodine molecule is having 0 oxidation state, and I minus is present here in -1 oxidation state. So this is the paradox of fractional oxidation number. Look at the second question. You need to calculate the oxidation number of sulfur in H2S4O6. So hydrogen, we know it's present in +1 state. Sulfur, you need to calculate 2 plus 4x minus 12 is equal to 0, and x comes here out to be 2.5. If you look at the structure of H2S4O6, here first sulfur is present in +5 oxidation state, second sulfur is present there in 0 state, third sulfur is present in 0 state, and the fourth sulfur atom is present there in +5 oxidation state. So +5 plus 0 plus 0 plus 5 upon 4 comes out to be 2.5 respectively. So here when you draw at the actual structure, you come to know the oxidation number of each sulfur atom that is present there. Then the third part, you need to calculate the oxidation number of iron in Fe3O4. By stoichiometry, Fe3O4 is a mixture of FeO and Fe2O3. FeO, iron there is present in +2 oxidation state, and in Fe2O3, iron there is present in +3 oxidation state. But overall, when you calculate the oxidation number of Fe and Fe3O4, it comes out to be 8/3 respectively. But by stoichiometry, iron there is present +2 oxidation state in FeO, and iron is present in +3 oxidation state in Fe3O4. You need to calculate next oxidation number of carbon in CH3CH2OH. So CH3CH2OH is having the molecular formula C2H6O. So here you need to calculate the oxidation number of carbon. So 2x plus 6 minus 2 equals to 0. So x here comes out to be -2 respectively. By chemical bonding, C2 is attached to 3 hydrogen atoms. Here you can see C2 is attached to 3 hydrogen atoms, that is less electronegative than carbon, and one CH2OH group that is more electronegative than carbon. Therefore, oxidation number of C2 is equal to 3 plus 1 plus X plus 1 into minus 1, because this is more electronegative than carbon. So this whole group will have the oxidation number of -1 respectively. And the oxidation number of carbon C2 comes out to be -2 respectively. C1 is attached to one OH group and its oxidation number is -1, and one CH3 group whose oxidation number is +1 respectively. Therefore, oxidation number for C1 on calculation, here it comes out to be -2 respectively. So this is how you will be calculating. By drawing this structure, you can calculate the oxidation number for each element that is asked. Then in CH3COOH, you need to calculate the oxidation number of each carbon atom. When it is written in molecular formula C2H4O2, carbon here comes out to be 0, the oxidation number. But by chemical bonding method, C2 is attached to 3 hydrogen atoms, that is less electronegative than carbon, and one COOH group. Therefore, oxidation number of C2 equals to 3 plus 1 plus X plus 1 into -1, and the value of X comes out here to be -2 respectively. Whereas C1 is attached to one oxygen atom by a double bond, one OH whose oxidation number is -1 and one CH3 oxidation number is +1. Therefore, oxidation number of C1 equals to +1 plus X plus 1 minus 2 plus 1 minus 1 equals to 0, and the value of X comes out here to be +2 respectively. This is how you will rationalize your results, and you will calculate the oxidation number by drawing the structure, and you will give the explanation. Hope it's all clear. Thank you, children. In the next class, we'll be studying about the balancing of oxidation and reduction reaction, that is redox reactions. Till then, thank you and have a nice day.